Yeah. But okay, so let me catch you up real quick and then we'll go back to what we were doing. So we're on chapter 9. We're doing mass spec and we're going to do a couple practice problems, but we're going to do a brief concept intro of what mass spec is. So essentially what we've covered so far is that mass spectroscopy is going to tell us the mass of a compound, obviously, and through the mass you can figure out what the formula is. And the way this works is we take a molecule, such as the one drawn here, and we blast it with a laser. So the laser is going to, bam, hit this. And when we hit it with the laser, we are going to break apart the molecule. So what we were just saying is that we can basically break it at any of these bonds. Like theoretically, you could break any of them. But the most stable way to break it would be this one. And the reason is because we want to have the charge on a tertiary position, because tertiary is better at holding a charge than primary is, and secondary is. So something that you're going to need all semester, we'll write down right here. What is the order of stability when we're talking about primary, secondary, tertiary, whatever?
It's tertiary, secondary, primary. And this always kind of, I mean, most of the time I'm okay, but for the like when that bond breaks, you get a carbocation and the radical too, right? The radical in where does the radical go in this particular one that you just did?
Okay, so what I was going to say is I know Dr. West explains it in the super scientific way, but I'm just going to give you the most bare, simple way. So, what I like to think about is cool. We know that it has a charge, so all we're going to do is ignore the chlorine and we're going to replace that charge with a radical. And we're going to end up with our tertiary radical.
Wait, I'm okay. I got a little bit confused there because the way that I can't, God, I'm like trying to jog my memory from that long ago because I thought that you wanted to like the carbocation stability is what you go for first. I remember that's what we did in Orgo 1 when we were breaking the molecules apart.
Yes, but
And
here,
then
the best
Mhm.
part is the stability order is the same. So that's why when I tell you guys to do it, I say just like simplify it and pretend they're the same and just use a radical to begin with. Don't even go through the ions just because it's more complicated than you need for this class.
Okay.
I know that might not be a satisfying answer if you really want to know how it works, but the stability order is still exactly the same. Primary is least stable, tertiary is most stable. And
Yeah.
then something you won't need for this exam, but I'm just going to write here so you note for later. Look up the allylic and benzylic positions for next
Yeah,
time.
the allylic one was the one that was like right after, because we did that for radical reactions in chapter 10, and the allylic
Mm-hmm.
one was the one that was after the double bond, right? Yeah, that place. And then the benzylic one was on the ring. Um,
Yep,
what
so
was
it'll
it?
be
It was
right here.
yeah, yeah. Okay, now I remember.
Awesome. Yes, so it's going to be one away from the ring. And this is going to be the super most stable, then this one, then tertiary, secondary, primary.
Okay.
But this is just on the side. You don't have to worry about it for right now. It won't be on this exam. Okay, now that we've got that covered, this is going to be our most stable radical. And we have a very special way to, I guess, denote this radical. It has its special peak, actually. Do you happen to know what that peak is called?
The most stable one is the base peak, right? It's the one that you have the most of.
Awesome. Yes. So I'm just gonna write um, main aspects. So you can kind of think of it the same way you do NMR. You can like organize it similarly in your mind. So the main aspects, we have four main peaks. And the first one, as you said, is the base peak. And we know that this is the most abundant radical. Sorry. It's the most abundant fragment, which is the most stable radical. I know it's hard for you guys to read and write it while I'm zooming in and out. I really apologize for that, but it's going to be so sloppy if I don't do that.
Yeah, no, no worries. I'm not writing it at the same time. I just try to pay attention to what you're doing because
Okay.
if I try listening at the same time, I don't absorb it as well.
Okay,
The only
awesome.
thing that I'm getting like confused about though is that I thought that like not that it was supposed to represent the most abundant fragment of or most stable cation, not the radical. Am I getting confused or
So, to be completely honest, mass spec is one of those concepts that I don't know all the real science behind because he never cares beyond the super like surface level. So as far as I learned it, you can essentially think of them as being the same. So the
okay,
base
okay, that
peak
makes
is
sense.
just, yeah, it's the most stable piece, which is going to
Okay.
be the same either way. Yeah.
Yeah, that's good enough. That makes sense.
Okay.
Okay, perfect.
Cool. Perfect. Also, hello, Sarah. We are doing mass spec right now, so if you have any questions or you want me to catch you up at any point, please let me know. All right. Moving on. Just scratched myself really bad. Okay. So, do you know what the other peaks are called? There's going to be four in total.
I know there's the parent peak, or I forget which one that is, if that's the M plus, is that the M plus one?
So, we have the M plus peak, which has two names. It is the parent peak, aka, do you happen to know what the other name for it is? Maybe?
Molecular ion?
That's the one. I don't know why they give things a bajillion names, but the parent peak, aka the molecular ion, aka the M plus peak, is simply going to tell you how much carbon and hyd- oopsie, before I even say that. That's essentially going to tell you the mass of the entire compound. So since we're in organic chemistry, we're mostly going to deal with hydrocarbons and heteroatoms and things like that. So all of our compounds are going to have an M plus peak, right? And after the M plus peak, you mentioned the M plus one peak. So the M plus one peak is literally going to be 1 unit down from the M plus peak. And this is going to tell us more information about our carbon and hydrogen isotopes. And the reason I kind of wrote something and then erased it is basically because what's the most abundant isotope of carbon?
Um, the most abundant, is that the 13 one or no?
That's going to
Or
be
is it
carbon
12?
12.
12.
And so what M plus 1 is going to tell us is essentially the carbon 13. Oopsie. Carbon 13. So you guys might not know this, but do you have any idea what the abundance of carbon 13 in nature is? Like
Wasn't
what?
it? Oh, wasn't it like 1% or something? It's like a small amount or something.
Yes. So we know that 1% of every compound is essentially going to be carbon 13, or statistically speaking, it's going to be carbon 13, right? And so that's why every single molecule we look at is going to have carbon. So it's going to have a teeny tiny M plus one peak. Next to that, some molecules will have an M plus two peak. So unlike M plus one, every molecule is not going to have this. But if something does have it, sorry guys, it's being annoying. If something does have this, it's going to indicate either an oxygen, a chlorine, a bromine, or one other thing. Does anyone have any idea?
Sulfur?
Sulfur, exactly. All right.
Can I
So,
ask you something really quick about that? Sorry,
yes,
just
please do.
while you're on this one. Is it when you have the M plus two peak, that includes the carbon part, like the M plus one peak, would that have like the weight of these other guys? Oh yeah, wait a second. Parent peak, that's the one that's the entire mass of it. I guess the difference that I'm not really sure on is the M plus one peak. Would
Mhm.
that include the weight of the oxygen, the sulfur, chlorine, and bromine and that value as well, or no?
So here, let me,
Okay.
when I'm done just defining this, I'm going to draw a spectrum out, and that'll probably help you visualize it more. If you're still having that question, ask me again after, okay?
Yeah, no problem.
Okay, cool. Um, so yes, for oxygen, sulfur, chlorine, bromine, I'm going to explain more about what this means in a second, but we have to pay attention to specific ratios, right? So, does anyone remember the values or any idea what those ratios mean?
I think chlorine was it like 3 to 1 or
Yeah, so I'm going to write 33%. Do you remember what bromine was?
1 to 1?
Exactly. So this is approximately like 99%. Sulfur and oxygen are super, super, super tiny. I believe oxygen is like 0.1%, or 0.01, something like that. And this is like 10%, something tiny like that. So oxygen and sulfur, the ratio doesn't matter. Just know it's going to be really tiny peak.
And when you say ratio, that's in comparison to the parent peak or like
Exactly.
okay.
The
Yeah, that's
parent.
I always like forgot that part. It always confused me.
Yeah, and a
So
lot
it's
of people do get confused, and it makes it a lot more difficult because this can be super straightforward and easy to answer if that idea makes sense. So, what I like to write it out as is our ratio is going to be 3 to 1. And that means m plus 2, m plus 2 ratio. And
okay,
here's
that's wonderful that you wrote it out like that. That's how I need to see it. Thank
good.
you.
You're very welcome. I always write things out as if it's for me, and I love to spell things out. And so that's what makes sense, and hopefully it helps you guys as well. All right. So this is basically everything you need to know about all the peaks and what they mean. And so I'll keep that up for 1 second in case you want to screenshot or anything. Um, so Sarah and Peter, you weren't here last time, but do you guys by chance use Notability?
Yeah, I use Notability. I just I thought I booked a session for 11:30. That's why I didn't show up last time.
Oh no, that's completely okay. So basically what happened, sorry, basically I should have explained this better in my email. So I have two sessions on Wednesday back to back, and I know it doesn't allow you guys to book two sessions one after another. So and I hate kicking people out because like if you only have time on one day, I'm not going to force you to leave or, whatever. So I will always send out the same link for both hours so that if you want to, you can come early and go to both, or you can come at 10 and then like stay for the second hour. Um, Completely fine with me. As long as you show up at some point to the session that you signed up for, I can mark you as present. The only problem is if you don't show up to any of the ones and you did sign up for an appointment, I have to mark you as a no-show. And I think after three no-shows, it doesn't allow you to book any more appointments. So that's kind of how the system
Oh,
works.
oh, okay, yeah. No, I just wanted to make sure because I was like, because I panicked for a second. I was like, oh no. But thank you for that. And then I was actually watching your YouTube video on this, and you said that it was for sulfur it was 4.4 instead
Oh,
of 10.
you were probably right. I honestly didn't remember off the top of my head. Let's say 4.4.
No, I just
Um,
wanted to make sure that I had the right info.
yeah, yeah, yeah. I always just, if I don't remember the exact one, I just put 10 because I know it's less than 10%. So it's good that you know the exact number, but if you just know in general less than 10%, you're good. And then no problem at all. The question was, at what point do we need these peak information and these statistics? So I'm going to show you right now. I know this can be very confusing when you just don't have anything to compare this to, but it's more confusing if I just draw it out and you have no idea what I'm talking about. So, and also while I'm drawing this, the reason I even asked if you guys have Notability is because at the end of tutoring sessions, I found it's easier if I just like share this document with you. Excuse me, so you can go back and look at it. If you don't have Notability, I can send it to you as a PDF or something. We can talk about that at the end though. All right, now that I had my little spiel, let's go back to this. So let's say arbitrarily, actually, let's use this example. So let's say our original compound is this, right? What's the mass of chlorine? Can someone tell me?
Chlorine 16.
16, okay.
Oh wait, that might be oxygen.
Oh yeah, that is oxygen. I think it's 35.
Yeah, I was gonna say, I was like, wait, I think that's too low. I can check the periodic table real quick. Hang on one second.
Okay, please do.
Yeah, chlorine's 35.45 or like 36. I'm not sure, whichever.
Okay.
35.45 is what it says on the
Okay,
periodic
cool.
table.
So I'm just going to write the mass of this is 92. And this is the molecule we're looking at. And we already did this before, but our most stable fragment will be this guy. So, um, the scale here is not like mass spec where there's a set NMR where it's like a set scale. It can pretty much be anything because it really depends on what the mass of your molecule is. So let's say it goes to like 100, and let's say this is 90, and so let's say this is 70, whatever. Um, Usually it'll be like smaller and it'll be like 0 to 100 or whatever, but I want to make it bigger so you guys can see. Um, just because I started with 70, don't assume it always starts there. That's my disclaimer. All right. So, what is the mass of our most stable radical? What do you guys think? And you don't have to do the actual math, just tell me what your idea is.
The whole thing you said was 92?
Mm-hmm.
So then it would be wouldn't it just be 92 minus 36? So 56?
Yes. Okay, so I use the mass as 35 um, for this example. So I'm just going to write 92 minus 35, which is 57.
57, yeah.
And you obviously,
Excuse me.
like, yes, what's up?
So the 57 comprises of all the carbons, the mass of the carbons on this,
Yes, so it's the carbons and the hydrogens.
the hydrogens. Okay.
Yes, precisely. So the reason I wrote this out is not because I don't think you can do math, but because I want you to keep something in mind, right? So whenever you see m plus 1 or m plus 2 or m minus whatever, it's purely just saying the full mass is m, and then we're going to go this many units in either direction. So minus goes this way, plus goes this way. So at units 57, so let's say that's 57 units, right? Let's say this is 91, 92, 93. And you know what? I'm just going to change this around because my math, like how I did the scale, made no sense. So now instead of going 70 to 100, we're just doing 50 to 95. Sorry if that caused any confusion whatsoever. But okay. So, are you guys following me so far? I feel like I babbled a little bit at the end. I want to make sure I didn't.
Yeah, no, I'm good. I'm
We're good?
following you.
Okay.
Mhm.
All right, cool. And so at 57, we have the most stable peak, or the most stable fragment, right? And all you have to know is that the base peak is going to be the tallest one, and it's going to be at an abundance of approximately 100%. So the base peak is always going to be at 100 or close to it. So I will label base peak. All right, so next we have to fill in the m plus 1, and m plus 2 if we have it. So at what number are we going to have our m plus peak?
That one would be at 92, right?
Exactly, and how do we know it's at 92?
Because that's the parent peak, like the entire molecule.
Sweet. Okay, so yes, at 92, we're going to have this right here. And we can call this M plus, or parent peak, or molecular ion. All right, so at what space are we going to have the M plus 1 peak?
The m plus 1 would be at 93.
Yes, perfect. Okay, and I mentioned this, right? So how tall is this peak going to be?
Okay, so you said the m plus 1 peak. How tall is that going to be?
In comparison, like you don't have to give me an actual height, but like
Yeah.
Does
So
it get shorter?
exactly, it's going to be super, super, super tiny because it's 1% of the M plus. So we're going to make it like that. That's not actually 1%, but I still want you guys to be able to see it. So it's
Do
called
you mind
the,
doing me a favor, Rosemary?
yeah, what's up?
Would you write next to that 1%, would you put of M plus peak next to it, just so when
Yes,
you send it to us that I can remember that?
absolutely I can.
Thank you so much.
Okay.
Does that mean M+2 is gonna be like very, very almost non-existent?
Why do you say that?
I mean, since M plus is shorter than the base peak, and M+1 shorter than M+2 might be shorter than M+1.
Okay, that's a really great way to
I
think
might be
about it.
wrong.
I like the logic, right? And I like that you're putting them like the ideas together. But the only comment I have is we're not necessarily like going shorter as we go on. It really depends on everything compared to M plus, right? So we said here that chlorine is going to be 33%. And the reason we say that is because the abundance of the chlorine isotope, excuse me, in nature is approximately 33%. So all this means is that in this molecule, we have one chlorine, and that one chlorine is going to make an M+2 peak that is approximately 1/3 of the M plus. So this one will be approximately 1/3 the height. And I don't even know if that's actually
Say
like,
that last part again. I'm sorry.
yes.
Why was it 1/3 the height? Or what was 1/3 of the height?
I'm so sorry. I'm just going to fix this because it's going to kill me. All right. So, yes, I will explain this basically one more time. So, in nature, we have a natural abundance of each isotope, right? And on mass spec, all these percentages and everything are talking about the natural percentage of isotope. So, if we have a chlorine in the molecule, it's going to create an M+2 peak because approximately 33% of that compound is going to
Oh, you were
have,
talking about that.
yeah, exactly. So
Okay.
it's
Okay, the 1/3 of the parent peak because of the 33%. Okay, that makes
exactly,
sense. I
exactly.
I like zoned for a second, so when you said one, I'm like, wait, what did she say? Sorry.
Yeah.
Excuse me.
Yes. What's up?
So basically, using the stats above the graph, you're using the stats which says M+1, carbon 13, and all that. Is that what you're using to create the graph?
Exactly. Exactly. And so that's why your question was such a good segue because we're using this information to basically plot the spectrum. Or because you guys aren't going to have to plot one, but if he shows you a spectrum, you can pull all the information you need out of it.
And in these, like, is everything from the M plus up to the M+2 is going to essentially be the entire thing, not a fragment, right? Like the
So
base peak one is going to be like everything kind of before that would be like fragments, essentially.
exactly.
And
So
then, okay.
sorry. So basically, it's not going to be this pretty. There's going to be lots of like random lines scattered like that. And all of these are just going to be masses of different possible fragments, right? And as you said, this is a total compound. And so, as we can see, the mass is getting higher. So essentially, we are counting the mass of the whole product. Plus, we're going to put the isotope information in there.
Okay,
So,
gotcha. And
yeah,
I think I remember them saying from Orgo 1 2, that sounded like Orgo 1.
yeah,
That was like that sounded kind of confusing. That the M plus peak is going to be like, say for example, if he gave us one of these, that the M plus peak is the tallest peak that's the furthest to the right. That's how we like can identify it. And then to find M+1, you just go one mass unit up. M plus two math. Okay, now
Exactly. The other
this is
thing
like
I did want to point out though, I have like two like side things that I want to add once we understand this part, right? So a tricky little thing that they can do is the base peak can sometimes be the same as the M plus peak. So they're not always the same, but sometimes they can be. So if we had something like this, right? Except we don't have that. We have this. Now, this pink one is both the base peak and the M plus peak. And everything else would be exactly the same.
okay, and that just basically means that the molecule like didn't fragment or whatever. It's just the entire molecule itself
Yeah, so it's basically saying the most stable possible thing is
is
no fragments. So the way it is naturally, yes.
okay. Okay.
The other thing I want to mention is so I didn't write this before because I wanted you guys to not get it mixed up. But basically, M plus 1 also includes nitrogen. But when we're thinking about nitrogen, we're not going to look at the M plus 1 peak. Instead, we're going to look at the mass. So I'm going to do a star here. When we have nitrogen present, we will have an odd mass. So again, even though nitrogen is technically covered in the M plus 1 peak, I just want you to think of M plus 1 as carbon and hydrogen, and that makes sense why it's a 1%, right? However, he will try to trick you by adding a nitrogen in there. So while nitrogen doesn't change the M plus 1 peak, it is going to change the total mass. So if you have an odd mass, that indicates an odd number of nitrogens present.
But where would we, so if we like, we would be able to identify that there's a nitrogen if we have an M plus 2 peak, or how do we know?
So no, real quick before I answer you, hello Jordan. You are not super late. I am just finishing up the concept from the 10:30, and just give me like 2 more minutes, and then I'll start over, kind of. Okay, so to answer your question, no. So nitrogen is only covered in the M plus 1 peak. So having a nitrogen will not create an M plus 2 peak. This will essentially not change. You'll only have these two and you won't have an M plus 2. So the only way you can really tell is if this number here for the M plus peak is odd.
Okay, so I'm going to repeat you just to make sure that I
Yes.
understand. I don't know if you would mind writing it under that, just so if we have a nitrogen, then we won't have in the molecule, then we won't have an M plus 2 peak.
Yes.
We'll just have an M plus 1 peak. And then if that number is odd, then that means we have an odd number of nitrogens.
Mm-hmm.
Okay, got it.
Precisely. And I'll show you some examples as well. Because with mass spec, this is helpful. However, it's, better when you see an example. And so I'm just going to draw a little arrow here so everyone knows what this example is for. So, la-di-da. EX. All right. Doo-doo-doo. All right, so it is 11:27. So I'm gonna pause for a second. I am gonna zoom out so you guys can see the whole thing if anyone wants to screenshot or anything. Um, and there should be a couple more people joining for the 11:30. So I might just give it a minute to do my spiel because I know people aren't here yet. So I take it back. I'm gonna take a minute before I do my spiel. Does anyone have any questions, comments, or concerns though? About anything. Doesn't even have to be just mass spec.
No, but I think you did a great job at explaining that, so thank you.
Thank you. I'm so glad.
To be a teacher, is that what are you said you're a bio major?
Yes, so I was I was a neuroscience major actually. Um, I am finally done with school. I am a pre-med, so I'm on that track, but I do really, really love teaching. I just don't think I could do it forever, you know?
Yeah, but you're really good at it. Who knows? Maybe like you
Thank
could teach
you.
at a med school or something.
Yeah, I definitely think once I get to a point where, I have my practice, whatever, I would definitely like to teach at least like 1 day a week or something because I love physicians who like don't just sit in an office all day. Like they have 1 day where they do research, 1 day where they teach, and then they practice the rest of the week. And I'm like, yeah, that's the life.
For you, yeah, because I think you would be really good at it.
Thank you so much. Yeah, it's one of those things also where like I do love medicine, so I would love to teach medicine. Um, and I do really like orgo, and I hope you guys can tell when I do it. It like I do really care about it. It's just like there was like 5 semesters in a row where I did it, and afterwards I was like, I cannot, I can't look at this anymore. It's
That's
so
funny.
much. Yeah, and like I totally understand now where all the orgo professors come from because they're just like so sick of it, and I'm like, if I taught it every day for 10 years, I would probably be sick of it too. But sometimes
Yeah.
they're just so much. All right, so I am going to stop the recording so I can